Hello, welcome to Designs for the Edge with Microchip Technology. Designs for the Edge is our ongoing live stream series in which we talk about market trends and system design challenges. We are live streaming today. Feel free to like the episode, share the episode, make comments, and ask questions. We'll try to take some of your questions at the end of the episode. Thanks for joining us. I'm your host, Eric Glatfelter. Today we'll be talking about optimizing motor control for energy efficiency. Joining me in the studio today is Pramit Nandi. Pramit, welcome to Designs for the Edge.
Glad to be here, Eric. Thank you.
For our viewers today, would you describe your role here at Microchip?
Sure. So I'm product marketing manager at Microchip with one of the microcontroller BUs, which focuses on digital signal controllers. And we tend to focus a lot on the motor control applications.
Okay, so let's talk motor controls. First of all, where are they? How important are motors in our everyday life as consumers, but also as users of industrial production?
Sure. So if you look at all around, motors are pretty much everywhere, in the studio, in our homes. So in the form of either appliances, your washer dryer system,
yeah.
your dishwashers have motors. You use your pool pumps and everything, they also have motors, right? And then you travel in a car.
Yep.
Cars have lots of motors.
Yeah.
Yeah, whether it's an internal combustion engine or electric vehicle.
Right.
So they tend to have anywhere between 40 to 100 motors,
okay.
depending on the type of car and the level or trim, right? Okay. And then you have vacuum cleaners in your home. And if you work in a factory environment, you will find robots.
Yep.
And guess what? Robots have multiple motors on it. So
yep.
Motors are pretty much everywhere.
Motors everywhere, and lots of things have many motors in them.
Yes.
Okay. So when we talk about optimizing the efficiency of that, how big an impact are we talking about on the energy supply?
So as we saw, there are motors everywhere, right? So according to an estimate of Energy Information Administration, so roughly 50% of our global energy consumption goes into the motor energy.
50%?
Yes.
Okay.
Exactly. And of course, if you go to industrial application, that might be a little bit more. It's
sure.
like more north of 80%. So if you look just within the US,
yes.
right? If you look at one of the charts here, in 2022, the total energy consumption in the US overall for 1 year was 4.07 trillion kilowatt hour.
Trillion kilowatt hours.
With a T,
okay.
Exactly. Now, if you divide it by 365 days, roughly you get about 11.2 billion kilowatt hour
okay.
per day.
Okay.
Now, as I said, 50% of that goes to motors.
Yep.
So the daily consumption for motor goes to 5.6 billion
right.
kilowatt hour, again with a B.
Yep.
Now, assume that if you improve the efficiency of all of these motors just by 1%,
mm-hmm.
so you can save 56 million kilowatt hours of energy every single day.
Per day.
Yep.
Okay. Big numbers all around, huge numbers all around.
So that's the impact.
Okay, so how do we get about saving that 1% or more? What are the design trends that are in play today to increase motor efficiency?
Sure. So there are four major trends, I would say. The first trend being people are trying to switch to efficient motors. They are switching from traditional motors like AC induction, AC motors, to BLDC or PMSM or IPM motors. Right, so those are more energy efficient, and for traditional motor also they are improving the materials so that
okay.
the efficiency is going up.
Okay.
So that's the first trend. Then the other trend that we are seeing is basically use of drives. Mm-hmm. So this has been going on for past 2 to 3 decades now, but it's more prominent now than it was before. So people are using variable frequency drives to drive these AC induction motors. Mm-hmm. People are using better technology or power electronics, because, for example, switching from IGBTs, which have been used in the past, to silicon carbide, which can switch faster and be more efficient.
Yep.
So that's the second trend. And the third trend being the algorithms. Mm-hmm. So just by having the motor and the hardware is not enough.
Yep.
To extract the maximum efficiency, you need to use advanced algorithms.
Okay.
Yep.
Okay.
And then last but not least is integration with IoT, mm-hmm. using sensors, and using AI and ML technology to detect errors or issues with the motor beforehand, so that you don't run into issues in the future.
Okay, so let's dive into each of those in a little bit more detail, right? Let's start with the motor itself. Can you kind of walk us through the main components of a motor structure and what's going on there?
Yeah, so as I said, people are improving the materials in the motors. So if you look at the motor, there are definitely end bells, right, which are the covers. And the more important thing is the rotor and the bearing and the stator with the winding. So there are a bunch of materials which have been improved over the past century or so. So if you look at just the rotor itself as well as the coils in the stators and all, so people have migrated over a few decades ago from aluminum to copper, which has better conductivity, so more efficiency. And then the manufacturability has improved also the tolerances, right? So that helps also reduce the noise and increase the efficiency in some ways. Now the other side of things is the trend that we see basically in the motors is people are in the rotors and the stator, people are using amorphous materials. So they take, traditionally people use silicon steels, right? But they tend to have high eddy current and hysteresis losses. They are getting replaced by amorphous material like metallic glasses. They tend to have lower eddy current and lower hysteresis losses and thus increase in efficiency. And if you look at magnets, there are permanent, different type of motor, not this one, but permanent magnet. There's a lot of improvements there too, because stronger the magnet, more the torque, more the efficiency, right? So there are some rare earth material magnets like neodymium, iron, and boron type. So these tend to have very strong magnetic field. Right, but they are rarer, so not so much sustainable. So people are switching to some alternatives like aluminum and nickel and chromium based or ferrite based magnets. They are also having very good properties over the temperature range and good magnetic field. So yeah, lots of things going on.
Wow, so let me back up to one thing you mentioned which caught my attention. You mentioned tolerances. Does that lead to lower friction?
Yes,
better.
It does. In fact, you brought up a good point. So if you look at the bearings, right? People used to use the journal bearings. They have switched to ball bearings. Of course, there's lower friction, better tolerances, and as a result, help increase the efficiency.
So how's the technology evolving in these motors? What are what are kind of the biggest benefits that we're getting?
So if you look at the past 1 century, starting from all the way from 1910, so this is a very good demonstration of that. So this is a source from Hitachi, right, showing a 5 horsepower or 3.7 kilowatt motor. So how big it was in 1910 versus how much it is today. Right? So you can see significant reduction in size.
For same power level.
For the same power level, 5 horsepower. So it's roughly about 20% of the size of what it was a century ago. So that means it has gone lighter with the newer materials. And lighter materials, more efficient materials, so lighter means more efficient, of course. There's also improvement in the thermal insulation. People are switching to more insulated, better insulated material, and with high dielectric constant, so it gives insulation thermal as well as the electrical one. So if you think about lighter motors, they are more compatible now to be used in automotive vehicles, right? So reduce the weight,
smaller,
increase the
lower weight. We can pack them into more things that we use.
Exactly.
Yeah,
good point.
All right. So so what's let's talk about the impact of all this technology. What can this do? What can this deliver for the efficiency of a motor system?
So as I said, variable frequency drive, the use of that is on the rise, right? So this is a very good example from Anibal Tide Almeida and their team. It's a paper from 2005. So it shows how efficient you can make your system just by switching to a drive. So you can see the system on the top, input is 100, then you have the motor, which has some standard motor efficiency, say 90% or so. Then you have coupling, which is coupling to the motor. That has its own efficiency. So of course, not 100%.
There's losses at each step, right?
Exactly. So each step increases the losses. And then the pump efficiency itself, pump will have its own efficiency, and then you're controlling the flow rate at a constant rate by using a throttling valve. So in order to maintain a constant flow, your motor is actually running at full current. It's drawing full power, right? And it's giving constant head, and you're throttling at the output. So you can imagine how much efficiency is getting lost
Right.
in terms of friction, cavitation of the valve, and so on and so forth. So as a result, in the top system, 100 is out, 31 is output.
Okay.
That's the power, right?
Yeah.
And as a result, the overall efficiency is just 31%.
Yeah.
If you switch to a variable frequency drive, you'd look for the optimum efficiency point. You're always operating at that level.
Mm-hmm.
So as a result, input, it's not drawing the 100 current because you're
Right.
not requiring the whole thing. So 43%, 43 is your input.
Yep.
96% is the efficiency of the variable frequency drive. The motor efficiency, if you use a little bit more efficient motor, and that goes to 95. And then you get rid of the control valve altogether because you're throttling by changing the RPM and maintaining the flow rate. So input is 43, output is 31, efficiency is 72%.
Okay.
2 times better than the
Yep.
case one.
Yep. Huge. Okay.
Huge, huge efficiency.
Impressive. So how do we build that drive system? What are the components that go into it, and what does Microchip offer in those spaces?
So if you look at variable frequency drive, basically it has AC-DC converter on the front end. Sometimes you have also PFC, and then you have the inverter, right, which is basically driving your motor as a load. So the PFC and the AC-DC converter, of course, has different components: key drivers, isolation equipment. Then you have your microcontroller themselves, and then of course the power stage, right? The same goes true with the inverter also. You have the K driver, isolators, with different regulators, voltage regulators. All those components is manufactured by Microchip. Microchip provides solution for that. And it's not just the hardware, we also provide the software associated with that in the form of different ways, like it could be evaluation board or some other reference design. So yeah, we do help with that. The other missing part that I forgot to mention is about the sensors, right? Because to run a motor, you need to sense the current. You need to sense the rotor position. So we provide semiconductor solutions for those as well.
Okay, so let's talk a little bit more about the ecosystem there. You kind of hinted upon hardware is not enough anymore, but can we talk a little bit, like for example, about machine learning? How is that implemented, and how does that benefit the overall system performance?
That's a very good question, Eric. I'm glad that you asked. So we talked about sensors, right? Current sensing, torque sensing, rotor position sensing, and whatnot. So all these sensing, and there's also vibration sensing, right? Accelerometer too. So if something is wrong with your motors, it can lead to vibrations, right? You can monitor those vibrations. Something is wrong with the bearing, you have the similar issue. And you can monitor all those things, parameters, with the help of sensor, and put your data into a microcontroller which has the capability to process those data. And with the help of machine learning algorithms, you can determine if the motor is going to go rogue in near future,
right?
Or it might need maintenance. So that's called predictive maintenance, right? So that's another avenue. We actually have a demo about that as well. So
So I don't think too much about doing predictive maintenance on the motors around my house, but for something like a manufacturing facility or a high power motors that are in industrial production facilities, that can have a huge impact on uptime of the facility, can have a huge impact on costs, right?
Yeah, because of course, if you have a motor suddenly needs a maintenance and stops the whole system, your entire production lot stops, right? So that's a huge loss of money for the company. So yeah, with the help of predictive maintenance, you can determine when it's needed, and you can do regular maintenance. And also it helps with efficiency too, because by doing regular maintenance, you're making sure the motor is always operating at its peak efficiency level and peak performance.
Okay, so that's a kind of a specific type of algorithm, but can you talk more about just algorithms in general? How important are they to developing these systems? And again, what do we offer customers to make it a little bit easier?
So as I previously said, just having the hardware and the motor is not enough. To get the maximum out of it, you need the right algorithm, right? So traditional method of, say, controlling AC induction motor is variable V with a drive is V by F control, which is well known. They are low cost, very easy to do, doesn't require any complicated mathematical calculation. Then the next step, if you switch to a different type of motor, like BLDC or PMSM motor.
Okay.
So BLD, you can do 6-step commutation.
Okay.
So that's gives you very good torque. It requires some of them have sensor based, some of them are without the sensor. So of course when you need sensor it's more costly. When you don't need sensor, it's using the back EMF to detect the rotor position, then it's lower cost. Then there is also sinusoidal one, 6-step commutation, which gives lower noise because sinusoidal waveform in general gives lower noise. Then the king of all algorithms, where you find the efficiency, highest efficiency, is basically field-oriented control.
Okay.
And just like 6-step commutation, it could be sensored or sensorless. So depending on what type of motor you're using, PMSM or BLDC, you can implement that, gives high efficiency, low noise, and excellent torque and speed performance.
Okay.
So this is used in several applications in automotive, non-automotive, industrial setup, everywhere.
Okay. So there's a lot of components here, a lot of choices that you have to make to optimize for the power level and the right type of motor that you're using and the right system. How would a customer get started about this? We offer a lot of this information on the site, the website, I assume?
Sure. So in terms of supporting our customer, we can help our customer to help build first to validate the things, prototype it, and then get them to production.
Okay.
So there are different phases, right, where we can help them. So just to do with development and validation, primary level, we provide them different types of
Let's take a look
boards.
at some of these boards.
Yeah, I got some cool toys today.
Okay.
Right? So this is a development board called MCLV, 48 volt, 300 watt board. So if you look at it, it's basically an inverter, 300 watt inverter. It has all the 6 MOSFETs right here. And this is a plug-in module called dual inline module, DIM. It has the microcontroller. You can program this one and plug right in and do your evaluation for motor control.
Excellent. Okay.
Yeah. So this is the first thing to start with.
All right.
And if the customer is in the next phase, they need something to get started with right away. So here, of course, we provide demo code, right, to get them started, and then you can modify it as needed. The next stage is reference designs.
Okay.
So we provide multiple reference design. Of
Yep.
course, I couldn't bring everything, but I did bring some of them. So this is a good example. This is a low voltage ceiling fan. And it's basically has a flyback converter in there, integrated with a inverter in there, and you can spin a fan with it.
Okay.
So it's interesting that it incorporates field-oriented control,
Yep.
as we talked about, but it also has other features like related to fans. For example, when the fan is spinning,
Okay.
right, and you turn it off, now suddenly it's just spinning on its own inertia. So it's windmilling, right?
Yep.
And then using the back EMF it is generating, you can detect the rotor position and start back again.
Okay. So
And
you're
it-
not starting from a fully stopped position. You're starting while it's already
Rotating.
rotating. Okay.
And then when it's completely at a halt, to get it started, you need to detect the initial position of the rotor to get it started so that it doesn't spin an opposite hunting, right?
Okay.
You prevent that. So we call it IPD,
Okay.
initial position detection. That is also incorporated in the source code. So we provide the source code that
Okay.
goes along with it as well.
Okay. So I see that operates by remote, and we've got it in a circular form factor to fit the housing.
Right?
Excellent.
Right on there.
All right.
Exactly. We have a cool video actually for this one.
Okay.
Another cool example is this kick scooter
Yep.
reference design. This is for 350 watts, up to 350 watt. So it, of course, has again the FETs and the gate driver and the microcontroller. We provide the source code associated with it as well. This one is also using field-oriented control.
Okay.
And it can do Hall effects sensor-based one, also with back EMF both ways. Another cool thing is it also has regenerative braking.
Okay.
So which means whenever the motor is coasting, it dumps its energy back.
Okay.
And then does braking as well.
Yep.
So yeah,
Okay.
it's another great one. Then the next one is vacuum cleaner reference
Okay.
design. This is for a small stick vacuum cleaner.
Yep.
Again,
So
circular.
I'm noting the form factor again. So
Right,
ready to
fits
go.
in. Yeah, that's the difference, right? Because this one is for prototyping. This
Yeah.
one actually is more in the form factor, exactly.
Okay.
So this is about roughly 350 to 400 watt type of vacuum cleaner. The main thing is that you're running field-oriented control or sensorless back EMF based, and you can go up to RPM of more than 1,000 So,
Okay.
sorry, 100,000.
Okay.
Sorry, I was
Oh.
wrong. More than 100,000 RPM.
Yeah.
So because you need the high
You
RPM.
need that
to
high suction.
to
Okay.
suction.
Yeah.
And last but not least, this is a very cool one. This is a drone.
Okay.
So there you need, of course, so this is a drone propeller reference design.
Yeah.
So it doesn't have the ESC or other things associated to the balancing and all, but you need 4 of these to drive motors.
Mhm.
And yeah, so this also comes with a code, the hardware design file, all available on the website.
Okay, excellent. Wow, so thank you so much, Pramit. There's a ton going on there. It's
Yes.
very interesting, can have a huge impact on energy efficiency and a lot of things to navigate through. So I thank you for sharing your expertise with that.
You're
At this
welcome.
point, let's take a break. Let me take a look at the iPad here and see if we have questions coming in from our viewers today. So a couple things in queue. First of all, this is interesting. What environmental conditions can impact motor control efficiency? So I think it's the operating environment of the motor.
That's a very good question. I'm glad that this one being asked now because we didn't cover it. So in terms of environmental condition, there's temperature,
Right?
there's humidity,
Yeah.
and then there's loading conditions, basically, right? There's 3 things. So, of course, with temperature, the resistance goes up, which is well-known fact. So, if higher the resistance, you have more losses. So, as a result, the efficiency goes down. Humidity plays an important role because in terms of humidity, you can have corrosion in the connectors and all. That impacts the resistance as well, and can cause long-term issues and efficiency loss. Last but not least, loading conditions, right? Because if you look at a motor, torque, speed characteristic, you're supposed to operate at the most efficient point to get the highest level of efficiency.
Okay.
If your loading condition is changing, then of course the operating point shifts, and it may shift from to highest efficiency point to a lower efficiency point.
Okay.
So that plays a big role too. So it's always important to monitor these things in the
Interesting.
environment.
Okay. Our second question is, what role do sensors play in efficient motor control? And actually, in your answer you just gave, you were talking about temperature and humidity, which needs sensors, but
Yes.
you also mentioned, position sensors,
Yes.
current sensors, and things like that.
Yes. So sensors play a huge role. We touched upon it, as you said. There's temperature, there's humidity, there's of course this rotor position, and then there's current. All these sensors extract very important data about driving the motor,
Okay.
as well as monitor the health of the motor.
Okay.
So they are playing very big role nowadays. It's getting more important now. Yeah.
Okay. So those algorithms, the machine learning, things like that, obviously have to detect what's going on with the motor and the environment to be able to adapt.
Yes. So all of these parameters that we talked about can be fed into an algorithm for machine learning. For example, we have actually a demo.
Okay.
It uses a classification model
Okay.
to detect issue with the rotor or an unbalanced load. So if a rotor or bearing, for example, has something going wrong with it, so it can detect those issues. And in that one, actually, we don't even have to use sensors. In some cases, what we could do is, because if you're using field-oriented control, there are 3 different loops, right? There's ID and IQ. So ID is basically aligning with the magnetic flux. IQ aligns with the torque.
Okay.
So if you monitor the IQ current inside that, looking at the trends in that, you can determine if there's something wrong with the bearing or there's an imbalanced load. So we have a demo doing that. So it's a
Okay.
kind of predictive maintenance, right?
Okay. Interesting.
Yes.
All right. Let's see what else we have coming in. Next question is, how does predictive maintenance contribute to motor efficiency? Okay, so we talked about predictive maintenance, like of the efficiency of the factory, like you don't want the motor to shut down or anything like that. But can it also help just the energy consumption as it's in normal operating conditions?
So yes, so with the help of predictive maintenance, you're continuously monitoring these parameters. Any shift that is happening, you can actually adapt your algorithm to make sure that it is going backwards to the highest efficiency point.
Okay.
So you can do that in real time. That's
Yep.
one thing. And then the other, in the longer term, as we said before as well, right? Because you're continuously monitoring this parameter with the help of predictive maintenance. You can do regular maintenance to make sure the motor is always operating at its highest performance and highest efficiency level.
Right.
So that way, it helps with the overall efficiency,
Yeah.
maintain the efficiency over a long period of time.
Yeah, and again, in some of those environments, we're talking about extremely high power systems. So even a little bit of
Yes.
efficiency improvement can save
Yes,
save
we
a
saw
lot of
that.
energy.
Even 1%, right?
Right, right. Okay. So next question is kind of similar. How can advanced control algorithms improve motor efficiency? So is there anything that you wouldn't call machine learning that would be a more general algorithm that would help efficiency?
So yes. So we talked about different algorithms, right? Field-oriented control being the king of algorithm, giving you highest level of efficiency because it controls the torque and speed characteristics very well, and also gives lower noise.
Yep.
The other thing is that there are certain algorithms which help with reducing the harmonic distortion.
Okay.
And with that, of course, you get lower noise, but also helps in with the efficiency. But on top of this field-oriented control, there are multiple add-ons. We discussed about this windmilling, then initial position detection. There's also something called as zero-speed max torque, which we have released as a part of a tool called Motor Bench last year. So we support all those algorithms with that Motor Bench tool, as well as with different modeling tools like MATLAB. So in those cases, so there's another algorithm, for example, called maximum torque per ampere, right? And there's something called as field weakening. So maximum torque per ampere means, you can imagine you're getting more torque per every ampere of the current that goes in.
Okay.
So imagine that it's a electric bike or something, right? Some electric vehicle. So if you are designing your motor for the peak torque, so if whenever you need it, you are going to use that algorithm to get the higher torque. So that's your boost mode.
Okay.
And then if you want your efficient mode or a little bit of boost on the speed, you can do field weakening and achieve higher RPM for a little bit of small duration of time. So you can switch between these kind of modes in an electric vehicle, for example, using these add-on additional algorithms. So yeah, we support a lot of these things in our different tools.
With the algorithms. Okay. Okay. Let's go back. Let's see. Okay. Okay. So one I can relate to a little bit. Can you explain the concept of regenerative braking and its benefits in motor control? So probably I, like many people, think of that in terms of having a hybrid or an electric vehicle when we know that there's regenerative braking in the automobile.
Yes.
Can you talk a little bit more about that and the overall benefits?
Oh yeah. So we just talked about this e-scooter, right, which has regenerative braking. So regenerative braking is nothing but when the motor is coasting, spinning on its own inertia, it acts like a generator. So either you can dissipate that as heat energy or dump it back into the battery to charge it up. Right.
Okay.
So that way you can recover some charge back into the battery. It has its own benefits, of course. It in some ways help with the energy efficiency, but more important thing is you're extending the range because you're not wasting that energy and putting it back into the battery. So that's the second benefit. And the third important benefit, which people tend to forget, is because it's doing braking by itself electrically, so you don't have to use your brakes, mechanical brakes that often. So you don't have to change your brake pads that often.
Those physical pads aren't being used as much. Okay.
It's not just the efficiency, it also saves with the cost over long term.
Okay.
Right.
Interesting. Again, very complex, right? There's a lot of different contributing factors there and a lot of things to consider in the design. So,
exactly.
Okay. I think that is our last question. We'll break there. So again, Pramit, thank you so much for joining us. It's a fascinating topic. There's a lot going on in the design area right now. To our viewers today, thank you for joining us. We appreciate you taking some time out of your day to join Designs for the Edge. If you like the episode, please share it, like it, comment, and also please visit microchip.com/designsfortheedge. There you can see our upcoming episodes. We'll have an episode every week through October 16th for this season. We'll be posting information about upcoming seasons. You can sign up for notifications, and you can also peruse our previously recorded library of episodes. Again, thank you so much, and hope to see you next time.
Thank you. Thanks.